Okay, so we are just about at the cusp of starting inferential statistics for the semester. We've been focusing mostly on descriptive statistics, right? We have a distribution of data and we're trying to describe it, basically measures of central tendency, and then our measures of variability. But we're going to make the transition to inferential statistics. And I wanted to talk a little bit more about probabilities, and especially as they relate to the normal curve. Okay, so we have certain values on the x-axis, and remember that there's an implied frequency here, and remember that there are lots of blocks here, that is outcomes in our whatever measurement we're taking, or observations that we're doing. And I wanted to talk a little bit more about probabilities, okay, and how it relates to the normal curve. We know that the mean for a normal curve is here, and there's some deviation from the mean, and we describe that using standard deviation or the average variation. But relative to the entire distribution, this is what we see most often. That ends up being the mode, okay, which is at the same place as the median and the mean. But oftentimes we're going to use these as our gold standard for descriptors. So we can say in this case that when we look at a distribution like this, most of the time we're going to see the mean, okay? If we went in and put all of these blocks into a bucket and we were pulling out a block, the most likely choice that we would pull out is the mean, because there happens to be most of those, that is, most values at this x than any other x value, okay? Now we're going to get to talking to about that more, but let's use a couple of examples I think that people are more familiar with when they talk about probabilities, and that is, let's think about a deck of playing cards, okay? If we have a deck of playing cards, so there's 52 cards in the deck, right? That's the total number of cards. And I can ask you, what is the probability? Let's get rid of this for now. We'll come back to this. What is the probability that I would end up getting a queen out of a deck of cards? Okay, well, how many queens are there? There's 4 queens out of 52. This is unfinished business, right? I've mentioned this before, whenever you have a fraction. So 4 out of 52 cards, that's our probability. So the probability, and use your calculator, excuse me, the probability here is 7.69%. That is, we're going to divide 4 by 52, and that's what we have for our probabilities. So that's the chance of getting any queen, because there are 4 queens: diamonds, hearts, clubs, and spades. And so the probability of getting any queen is 7.69%. The probability of getting a heart, now remember, there's 4 suits in the deck, so there's 13 of each of the suits in a deck. So 13 out of 52, 13 divided by 52, and so that's 25%. And in fact, 13 out of 52 is 1 out of 4. 1 out of the 4 suits, okay? Or 13 hearts out of 52 cards, 25%. If we were looking for a queen of hearts, Of course, that's a single card in the deck. So if we were looking for Queen of Hearts specifically, that is not just any queen, not just any heart, but a single Queen of Hearts. And in fact, hopefully, there's only one Queen of Hearts in the deck, 1 out of 52. And so, let's see, 1 divided by 52, 1.92%. Okay. So these are some of the probabilities. When you're looking for probability, you're looking at how many items would match this outcome out of the total. 13 out of 52, 4 queens out of 52, 13 hearts out of 52, only 1 Queen of Hearts out of 52. Okay, and you can better believe that when I go to the casino and play poker, that I know these percentages, these probabilities very well. Of course, it's, you know, when I go to the casino, it's not a statistics course, and so I usually think this is about 8%. This is about 2%. Of course, this is 25%. If I'm looking for a specific card, if I needed the 7 of clubs to win the hand, I'm going to get out of that hand. It's only a 2% chance. Okay. If I need any queen, that's still sort of a low probability. I'm looking for any suit. That's still fairly low. Remember, 75% chance that I'm not going to get it. Okay, but poker players certainly know these percentages by heart, because if you want to be a good poker player, you need to sort of know your probabilities, and in fact, that's what I'm betting on. Now, anytime you pull a card out of the deck, it could be the Queen of Hearts. I'm talking about probabilities, okay? There's a difference between possibility and probability. There is a huge difference between something possible and something probable, okay? It's possible that a meteor could hit my house in the next hour. If I really thought that that was probable, I'd get the hell out of the house, because that's certain death if your house gets hit by a meteor. Okay? So there's a difference between probability and possibility. And we're going to make our decisions always on probabilities, okay, not possibilities. So there's a little bit about probabilities with a common kind of with playing cards. Everybody's familiar with those. We can also talk about probability when you're flipping a coin, right? I could talk about what is the probability that I'm going to flip heads when I flip a coin. Well, the probability is 50% if the coin is fair. If the coin is fair, the probability is 50% heads and 50% tails. Here's a weird thing, though. When I flip the coin once, it's either going to come up heads or it's going to come up tails. Everybody with me? This is kind of a weird thing for people to think about sometimes. When I flip the coin once, it's either going to come up 100% heads or 0% heads. That's it. Now, the probability that that will happen with a fair coin is 50-50, but the outcome with one flip is only 100% or 50%. Okay? The more I flip the coin, the more I can see sort of some details between 100% and 0%. If I flip the coin twice, I'm expecting half heads and half tails. If it comes up 2 heads, or if it comes up 2 tails, I wouldn't all of a sudden think that that coin is unfair. Okay? Let's look at the distribution. If we flip the coin 100 times, so here we have 100 flips of a coin, okay? if we do that a number of times, I mean, what do I expect to see? I expect to see 50 heads and 50 tails, right? That would be, for a fair coin, that would be the most likely outcome, the frequency, okay, the mode. Most of the time with a fair coin, if you flip it 100 times, you're going to see 100 heads, 50 heads, 50 tails, okay? If all of a sudden your friend has a coin and she flips 49 heads and 51 tails, or 51 heads and 49 tails, I hope that you wouldn't all of a sudden accuse your friend that they're using an unfair coin, right? Or if we go 48 and 52, or what about 60 and 40, or over here, 40 and 60, okay? And you can figure this out, actually, mathematically, but the chances of getting exactly 50 heads and 50 tails when you flip a coin 100 times, the probability of that happening is less than 8% of the time. But it happens to be the most frequent, that is, the modal outcome when you have a fair coin, okay? If we were to flip a coin 100 times and it comes out 95 heads and 5 tails, we're not going to use that coin to see who pays for lunch, right? Because, at least I'm not, because I think it's an unfair coin. The chances that you're going to flip a fair coin, 95 heads and 5 tails, is extremely, 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 extremely low. I mean, it's way out here, right? And so if you flip a coin and you're out in this area, then I'm going to question whether that's a fair coin. At some point, I'm going to say, I don't think that you have a fair coin. You see how this kind of aligns with our last video? That is, at some point, we're going to make a decision that that's a weird coin, that I don't trust that coin. Here's what is expected. Here's something I don't expect, right? If we're trying to assess what's going on with that coin, and we have some very unexpected, improbable, unusual, atypical, weird, funky, bizarre, right? Those are all words that would describe something that's abnormal, right? We don't expect it. It was unlikely to see that. So based on no other information, I would say, if we're out here or here, I would say, I don't think you have a fair coin. Now somebody might say, well, if I flip 99 heads and 1 tail, couldn't we get that? I mean, isn't that possible? And the answer is, well, of course it's possible. You're flipping the coin 100 times. And the coin doesn't remember, what it was the last time you flipped it, what the outcome was. It's possible that that would happen. But we're going to make decisions not on possibilities, but on probabilities. I mean, here's, and we do this all the time, folks. We do this all the time. And people sometimes use these interchangeably, and it's just not the case. I mean, here's what I would ask you. Is it possible that you're going to win $100 million in the lottery tomorrow? The answer is yes, it's possible. But I wouldn't give up everything and quit school and, spend all my savings because tomorrow it's possible that I'll win $100 million, right? I mean, we just don't make decisions based on possibilities typically. To be more dark and macabre, is it possible that you could get into a fatal car accident tonight? The answer is, unfortunately, the answer is yes, okay? If this is your last day on Earth you would probably, if you knew that, you would probably be doing things quite differently today. But the probability that that's going to happen is so low that we don't make decisions about our behaviors now based on the possibility that I'm going to win $100 million tomorrow, or the possibility that I may be dead tomorrow. Okay? I'm sorry, I hate to be so dark, but this underscores the fact that we usually base our decisions on probabilities. Every day you base decisions on probabilities, right? It's probably, you're probably not going to win the lottery. You're probably not going to die. Okay? The meteor may hit my house, but I'm not too worried about it because the probability of that happening is very, very, very low. Is it possible? Yes, it is. Yes, it is, for sure. I've seen people out on a golf course golfing when they're hearing thunder and seeing lightning in the distance. Is it possible that they could get hit by lightning? Yeah, for sure. Is it probable? Well, sometimes it is probable, and people don't even make a decision then, okay? But we all make decisions based on probable outcomes. And once again, I've been saying this a lot. The mathematics reflects that concept. Sometimes people think that math is totally unrelated to your life, and I'm like, it's nothing could be further from the truth. Whether you realize it or not, you're basing a lot of your decisions on probabilities based more than possibilities, okay? And speaking of this, because it's very much like a coin flip in a way, I want to show you something, and I hope that you can see this all right in the video. I have a little thing here. I'm holding it upside down, okay? This is a thing called, believe it or not, it's called a Quincunx, okay? And what I'm going to do here is there's 256 little ball bearings down here. I'm going to flip this upside down. The ball bearings are going to fall down through this array of blocks, and I'll show you what's happening there, okay? And we'll see something that's quite interesting here. So let's do this. So I'm going to just flip it upside down, and do you see the distribution? It's a normal distribution for the most part. So there is 1, 2, 3, 4, 5, 6, 7, 8. There's 9 bins down here. And we see that most of the ball bearings ended up in the middle bin number 5. Okay? Let's try this again. I got everyone started there. I'm going to flip it upside down. And what do we see? I'm going to make sure this is... there we go. What do we see? Middle bin. By the way, you see a normal distribution here. And if we look really closely, you can see one little ball bearing here, and 1 there, and maybe 4 here. More, lots more, and as we go, okay? Let me do this again. Same thing, okay? Let me do it again. Same thing, nice normal curve with the most in the middle, number 5. Now, I could make this a skewed distribution, by the way. If I just tilted it to one side, now we have a positively skewed distribution, okay? If I tilted it the other side, that is, I'm going to make a bias here, then I'm going to have a negatively skewed distribution, okay? But if I keep this nice and keep it nice and level, that's what I'm going to get. That's what I'm going to get, okay? Let's keep it nice and level. And that's what we get again. Okay. In fact, it'll be that way virtually every time I flip this over. And let me explain the dynamics here. This is extremely low tech. You can get a demonstration of this on the internet. But of course, whenever I'm looking at the internet, I'm wondering if somebody just programmed it to be like that. This is nothing but a piece of cardboard with this plastic design on here. And let me show you, or let me explain what happens. And I'll show you why this is like flipping a coin. So 256 ball bearings start up here. They come down through this little funnel. Let me see if I can get my pointer here. Well, right here, there's a chance, the probability that the ball bearing is going to go either right or left. There's a 50% chance it's going to go right, a 50% chance it's going to go left. Okay? Then it falls down, then it continues down here. Okay? And at this point, there's a 50% chance it's going to go right or left. And then goes down here, 50% chance right or left. Then it goes down here, 50% right or left. Then it goes down here, 50% right or left. In fact, there are 8 different places here where the ball bearing can go either right or left. At each of those junctions, the probability is 50% that it's going to go right or left. This is like flipping a coin 8 times. Okay? And in fact, this middle bin number 5, there's no direct path to bin number 5. There is no direct path to bin number 5. In fact, there's no direct path to any of these gravity's going this way. There's no direct path to any of these. If there's anything that's like a direct path, it might be right down here to this bin, and that's where we see the lowest number. Okay, let me explain what happens here. We have 8 choices as we go down through that the ball bearing is going to go right or left. At each of those choices, the chances of going right or left is 50%. Okay? In order to end up over here, the ball bearing has to go left 8 times in a row. To land here, the ball bearing has to go left 8 times in a row. Okay? For ball bearings to go here, 4 times left, 4 times right. That is, it goes to the right half the time and to the left half the time. That's the most common outcome. It's just like when you flip a coin 8 times. The most probable outcome is 4 heads and 4 tails. This is equivalent to getting 5 heads and 3 tails. This is equivalent 6 and 2 tails. This is equivalent to 7 and 1 tail. This is equivalent to 8 tails all in a row. This is equivalent to 8 heads all in a row. Very low probability. Okay? This is just a beautiful little toy, I think. Very low tech. And it shows us the probability that you're going to get 50 heads and 50 tails is the highest. And that is the mean of this distribution here in bin 5. Is it possible to get 8 heads in a row? The answer is yup. See that? But this is equivalent to doing 8 flips for 256 coins. Once in a while, once in a great while, 1% of the time, you're going to get 4 heads in a row. 8 heads in a row. Once in a while, there's only 2 in there, less than 1%. You're going to get 8 heads in a row, whatever the opposite of what I was just saying. Most of the time you get 4 and 4. Some of the time you're going to get 5 and 3 or 3 and 5. Okay? And in fact, there's no magic to this. There's no magnets. There's nothing electronic about this. I'm not doing any, funny business. I'm just putting 256 coins down there, and I'm saying, okay, what if we flip each of the coins 8 times? And there we go. Okay. Yeah, we got a few there. I think I might not have held it perfectly symmetrical or not. Okay. But here's what we're going to be able to do as well. Let's flip it again. And there we go. Okay. And I would ask you, can you make a bet? Can you do a bet now? Notice we're going to use probabilities for a prediction. If I start again and I try to hold it as straight as possible, where would you put your dollar if you were going to bet on which bin would get the most ball bearings? Where would you put your dollar? Bin 1, 2, 3, 4, 5, 6, 7, 8, or 9. I'll give you a second, okay? I would put my dollar on bin number 5. Okay. I mean, you're going to have to trust me on this one. Let me do this. I'm going to hold it nice and straight. Guess what? I'm a winner. And I hope you were too. Now, you don't want to be like my sister. She might put her dollar here. And I'd be like, why did you put your dollar there? Well, it could be that. They could all go there. I'm like, yeah, it's possible. It is absolutely possible. But it's not probable. People think this is made up stuff, or it doesn't relate to real life, or I don't know what people are thinking. This is a demonstration of what happens, but we're basing our daily decisions on probabilities, okay? We're basing our daily decisions on probabilities. My dog's probably not going to get hit by a car, but boy, if I thought, is it possible? Tomorrow, Is it possible? Sure. And I would be crying and hugging my dog, extra special, if I thought that it might, if there was a probability of the dog getting hit by a car. Is it possible? Yes. Is it probable? I hope not. Okay? So that's what I'm talking about here. Whether it's the Quincunx or flipping a coin or talking about playing cards, we talk about probabilities. We're going to make our bets. We're going to make our bets based on probable outcomes. Absolutely acknowledging that it's possible to flip a fair coin and get 99 heads and 1 tail. Wow. If you flipped a coin for me and you got 99 heads and 1 tail, my conclusion would be that that coin is probably unfair, that it's weighted on one side, okay? That's just the way it is. I'm going to say you probably have a coin that's unfair. Could I be wrong? Yes, I could be wrong, folks, okay? I'm going to say right now that my bet is a meteor is not going to hit my house this evening. I'm going to I'll bet $1,000. If somebody wants to bet me that a meteor is going to hit my house and I'm going to take that it's not going to hit my house, I'll bet $1,000. I'll bet $5,000. And I'm probably going to win. That 1 in a million chance that a meteor hits my house, I'll be wrong. But sometimes I just don't understand in society where people equate these two. I could turn that Quincunx over 1,000 times, and I would bet everything that I have in the world that if 1,000 times that we're never going to see the majority of the ball bearings in the 9th bin or in the 1st bin. This is not magic. Could that happen? Of course it could. But the probability is so, it's just astronomically small. Okay? So we're never going to say, I'm not going to make my bets on whether something is possible. whether it could happen. I'm going to try to make my bets on the most likely outcome, what's expected. This is the most likely outcome. This is pretty high. This is pretty high. This is pretty high outcome. This is not a bad outcome, okay? But at some point, enough's enough, okay? So, that's where we are. This is a little primer on probabilities. You should think about it, contemplate it a little bit more. If you need to, review this video, go ahead. You can also, there's lots of kind of introductory probability information on the intrawebs that you could potentially look at. But the idea here is we're going to use probabilities because we know probabilities, and in fact, we can start talking about these as not sleeping, folks, not sleeping, but as z-scores. And once we use z-scores, we know we can talk about all sorts of different distributions because this is our standardized, our unit normal table, okay? We could put the actual values in, or we could talk about z-scores. As z-scores increase, either positively or in the negative direction, it's less likely that we're going to see those outcomes. Okay? All right, so we are ready, I think, to do some inferential statistics, or at least develop the inferential statistic. And what I want to do here is talk about, remember, in inferential statistics, what we're going to do, we're going to infer, that is, sort of make some guesses, make some bets, if you will, right? Make some predictions. We're going to infer something about a population when we only have a sample taken from that population. Okay? I'm going to try to guess what's going on in the population. And when I say try to guess what's going on, I really want to make a guess about these two things. Okay? Because if we assume normality, these are our gold standards, right? And this describes the population. But I'm going to make my guesses about the population based on some incomplete amount of information, and that's called a sample. A sample is a subset of the population. Okay? So, let's try this. Okay? Let's take a population, and I'm going to tell you what this population looks like in terms of its distribution. It's got 25 scores in it, okay? And it's symmetrical, so it looks like a normal population. And here's what we're going to do. You can draw this in your notes as well, I hope. This is kind of a artistic way of doing this, kind of cheating here a little bit. Okay, and that's actually a population of 25. You can count them if you would like. There's 25 blocks there, and each of these blocks has a numerical value. Each of these blocks has a numerical value. There are 5 blocks with this x value. Everybody with me? 5 blocks with this x value. 4 blocks with this x value. 3 blocks with this. 2 with this. 1, 2, 3, 4. Okay? Of course, we know where the mean would be for this distribution. It's going to balance the distribution. And the balance point here, if all these blocks are the same size in this configuration, this is where the balance would be. Okay? Of course, we know, here's our implied frequency. We know that this x value is what we see most often. So we have, that's the place where the mode is at as well. And if we count the boxes, this is the point that's at the 50th percentile, where 50% of the boxes fall at or below. Just like any of these symmetrical curves that approximate normality, mean, median, mode is at the same spot. Of course, we know that there's some variability here. That is that not all of the blocks have this value. Okay? So good to go. So here's what I want you to do. What do you think the mean is for this distribution? It is a distribution, a known distribution. That is, I'm giving you this distribution to consider. I know what the mean is for these blocks. What would be your guess? Now, if I was doing this in a classroom, somebody might guess 70. Somebody might guess 85. And I'm like, all right, well, they might not be test scores. Maybe the mean is 127. Maybe the mean is 1,052. Maybe the mean is 3.673. Or maybe the mean is 107.53. Okay, we just don't know. In fact, any guess is as good as any other guess. Any guess is as good as any other guess because we have no information here except for what the distribution looks like. Okay, it's got 25 scores and here's how they're distributed. But as they say, anybody's guess is good in this situation. Let me put that on hold for a minute. Let me ask you to guess the standard deviation. What would the standard deviation be in this case? Now, in this case, you actually, if these are whole numbers, you actually could calculate what the standard deviation is. You could actually calculate it with just the information that we have here. And sometimes people don't believe me when I say that. They're like, what? How can you calculate? You don't know any of the numbers. I'm like, listen, the mean tells you where the numbers are in a number line. The standard deviation tells you how spread out they are. We can see how spread out they are, right? If I did this, just work with me here for a minute. You don't have to write this down in your notes, okay? If I put 100 here, and 101 here, and 102 here, and 103, and so on and so forth, okay? Could you calculate the standard deviation? That is, one person got 100, 2 people got 101, 3 people got 102, 4 people got so on and so forth. Could you calculate the standard deviation? The answer would be sure. If I put 5 here, and 6 here, and 7 here, and 8, 9, 10, could you calculate the standard deviation? The answer is sure you could. Guess what? If I put 100 here, 101, 102, or 5, 6, 7, 8, you would get the same answer for the standard deviation. If you don't trust me, if you don't believe me, try it out. Put 100, 101, 102, 103, calculate it, or put 5, 6, 7, 8, 9, calculate it. Why would they be the same? Well, I want you to think back, look at your notes. Remember when we used that example with, what was it, like 6, 7, 8, 9, 10, 11, whatever it was. We calculated the sum of squares for that group, and then we calculated the sum of squares for all those numbers in the 500 area. We found that they were the same variability. Well, it's the same thing here. I mean, here's how spread out the numbers are. This distribution may be down in the single digits, or it may be up in the hundreds. The standard deviation is going to remain the same. Okay? So we could actually calculate that. We're not going to do it right now. The means for those two examples would be dramatically different. Okay? Variability, we could calculate it. So I'm going to go back to the mean. What would be your guess for the mean here? Who the hell knows? And anybody's guess is as good as anybody else's. Okay? Because there's no way to verify it. There's no way to refute anybody's guess. So, here's what I want to do. I just happen to have another low-tech device here. It's a canvas bag. And this canvas bag is the population here. There are 25 wooden blocks in here. There are 25 wooden blocks. Each of the blocks has a number on it that corresponds to this distribution. So I'm going to go in and randomly choose. I'm mixing these up. I hope you can hear that. Mixing those up, I'm going to randomly choose a block, and the block has the number 14 on it. Okay? So somewhere in here is 14. Now I'm going to ask you to guess what the mean of this distribution is. Now, if this is part of the distribution, and it is, I would hope that you now would not say that the mean is 500, because it couldn't be. One of these is the number 14, and so 500 is out there. Let's see. Could the distribution start with the number 1? Well, if this was 14, 13, 12, 11, 10, 9, 8, 7, 6, no. So by virtue of this being 14, I know that the mean is not 1 or 2. So we have more information now than just nothing. Okay? That's the point of inferential statistics. I didn't know what the mean was before I had any information. Now I have some information. I have one block. Now, does anybody have any guesses for what the mean of this distribution might be? Now, if you said 14, we could even do this if we wanted to. If you said 14, I think that's a good guess. But that's just me. I think that's a good guess, right? That's what I would guess if I didn't know what the mean was for this distribution, and I pulled this 14 from the distribution. If I didn't know, my guess would be 14. But here's what I'm going to ask you. What is your rationale for making your guess the same as the block that we chose? Now, I have a rationale that I would use. Most people don't use this rationale, but they still might make the same guess. Somebody might say, well, because that's all that we have. We pulled out a 14, so that's going to be my guess. And I'm like, In fact, let me ask you this question. Is that convincing rationale for you? I hope that you would say, not really. It's not really convincing for me to say 14 is the mean, just because that's what we picked out. All right? I would say 14, but I have a different rationale, okay? Let's take a look at the probabilities of picking out one of these numbers, okay? What's the probability that we would pick out a block that has this number on it right here? What's the probability? And some people might say, oh, I don't know. Well, the reason I talked about the cards, the reason I talked about the coin flip is here's what we're going to do. There's one block with this number on it, right? There's one block with this number. Out of 25 blocks, so the probability that we would get a block with this number is what? Unfinished business, unfinished business. If you do the division here, the probability is 4%. Then we're going to pick out a block with this number. Okay? What's the probability that we would pick out a block with this number? Well, I'm not asking what's the probability of picking this block. The probability of picking this block is 4%. But there's two blocks with this number. There's two blocks out of 25 with this value on it. Right? There's two of them in there. So the probability of getting one of these with this number is double this. If we do this on your calculator, what you're going to get is 8%. What's the probability that we will get a block with this number on it? Excuse me. Well, now we have 3 blocks out of 25, and so this ends up being 12%, 16%, 20%, right? There are 5 blocks with this value on it. And by this value equals the mean. 5 blocks with the value of the mean. 5 blocks out of 25, that's 20%. Excuse me. Likewise, I mean, this is a symmetrical distribution. 16%, 12%, 8%, and 4%. The probability of getting a block with this number on it, since there are 2, it's 2 out of 25, and that gives me 8%. Okay? So we actually have our percentages here. Excuse me. We have our percentages because there's 25 blocks in this distribution. I showed you that they're going up in consecutive order, right? And so I have these probabilities. This is a given. Everybody with me? I hope. Take your time. Watch the video again if you need to. So, listen to my rationale here, because it's different than just saying, well, I picked a 14, that's all I had, so that was my guess. My rationale is this. It goes a little bit differently here. My rationale is the probability that I'm going to pick a block that has the mean on it is the highest of any of the other values compared to any of the other values. It is the most probable that I'm going to pick this. Is it possible that I pick this? Yes. Once again, probability is not the same as possibility, okay? Is it possible that I got this block when I put my hand in there and pulled it out? Sure. In fact, it's 4%, but the probability is higher that I picked out the mean. And the probability is still pretty good that I picked something near the mean. Think this through, because sometimes people are like, oh, I get it, you know? And sometimes it takes a little longer. It's like, when I put my hand in this bag, and I'm going to stir these all up. when I put my hand in this bag, what's the probability that I'm going to pick out a block with the mean on it, with the value of the mean? 20%. What's the probability I'll pick out one of these? 8%. What about one of these? 12%, 8%. Listen, I'm going to put my dollar on the most probable thing. The most likely thing I think is going to happen. The most likely thing. My dog's not going to get run over by a car. I'm not going to win $100 million tomorrow. A meteor's not going to hit my house, because that's really improbable. Improbable to get this. Is it impossible? No. But why would I put my dollar there? So when I put my hand in here, my best guess is that I pulled out the mean. Therefore, I think the mean is 14. Be careful, because sometimes people try to force the logic the other way around. I picked out 14, therefore it's the mean. No. My guess, based on probabilities, is that I'm going to pick out the mean. That doesn't mean that I did. Let's try it again. Okay, another block. This one is 15. Well, if I picked this one out first, my guess would have been that 15 was the mean, based on the same rationale, right? That the most probable pick is the mean. But you notice something? The mean can't be 14 and 15. So our guess changes depending on the block that we pull. Because inferential statistics, folks, inferential statistics means that you can be wrong. You're making a guess. What we want to do is try to optimize the probability that we are correct. Okay? With the Quincunx, I'm going to guess that most of those ball bearings are going to go right down the middle. Could I be wrong once in a while? Sure. With 256 coins, basically is what I'm doing. With 256 blocks, that's basically what I'm doing with the Quincunx. It's not likely that I'm going to be wrong. Okay? But the mean can't be 14 and 15. So we ran into a little bit of a problem here, but the rationale is rock solid, and that's what I want you to understand. I know I'm going a little over time, but we'll pick up in the next video. Since these have the value of the mean on them, and there's 5 of them, it's the mode, it's the most frequent. I'm going to guess that I picked one of these, but that it doesn't guarantee that I picked one of those. And the next video, we're going to develop a way to getting to be more confident that I have the mean for a population I don't know about, right? I mean, that's what we're talking about with inferences. Here's a population. You don't know what this population looks like in terms of the mean. We could figure out the standard deviation, but when we do research, we don't know what the population looks like. We don't know either of these. So we're going to try to make guesses from a sample to a population. That is inferential statistics. What we've been doing so far is pretty much descriptive statistics. When we have all of the information, how do we describe it best? Now we're going to make guesses. Wow. I'm hoping that you can anticipate that we're going to have to develop some pretty sophisticated techniques to try to make the best guess that we can. And we will always acknowledge that we can be wrong. We can acknowledge that we can be wrong, but we can increase the confidence that we're probably right. Okay? So we'll pick up on that. I'll show you a technique using this distribution, and we'll talk about how we can increase our confidence that we make a good inference about a population based on a sample, some subset.